Hey, this is Mr. Ferguson,
And Mr. Hunter.
and we're here to do the second lesson in Unit 12, where we're going to talk today about equilibrium constants.
Our first objective is to write expressions for the equilibrium constants.
And we want you to explain how the value of K, that's the equilibrium constant, would relate to the reactant and product concentrations when we're at equilibrium.
To find K given equilibrium concentrations of reactants and products.
And lastly, to find an unknown concentration if you know the value of K and the other concentrations involved.
All
right, so we've already kind of scratched the surface on this when we did the
Weak
Kas
acids,
and
yep.
KBs. So it's kind of an extension of that. It applies to other reactions and other processes as well. So let's get started.
All right, so we're looking at the equilibrium constant K. There are several different versions of K. There is Ka and Kb and Kw. We have seen those already when we were doing our weak acids and weak bases. We also have Ksb, which is new, and that is our equilibrium constant for a partially or slightly soluble salt. And then there's Keq, which is just the generic equilibrium constant as well for any form.
But the general way you find the K is the same for pretty much all of them. So just remember, going into this, we're dealing with reactions or processes that are reversible. So they can have a backwards rate as well as a forward rate, and the equilibrium's when the backward and forward rates are equal.
Yes.
Okay, also, we only consider reaction components that are either gases or are dissolved in a solute, like an aqueous.
Yes, and the things that are not considered then but not said, we have anything that's a pure solid, that's left off, and anything that's a pure liquid, we
So
leave
if it
out.
says S in parentheses or L in parentheses, we're not going to consider that as part of the equilibrium constant expression.
That's correct.
All right, so here's a generic reaction where we have A moles of A reacting with B moles of B. It's a reversible process, that's what that means. And we get C moles of C and D moles of D. So the little letters are the coefficients, the big letters would be the formulas. Let's look at how we write the equilibrium constant expression.
All right, so like the weak acids and bases, the products go on top. But now we have these coefficients included as well, which need to be included in the equilibrium constant calculation. So what we're doing is we're taking concentration of C raised to the power of its coefficient C, concentration of D raised to its coefficient D, divided by the concentration of A raised to its coefficient A, times the concentration of B raised to its coefficient B. These will...
So if the coefficient's a 1, you just put in the concentration.
Which is what we specifically did for the acids and bases.
We didn't look at any that didn't have 1 coefficients. Now we're going to.
We didn't want to deal with the quadratic equation, basically, at this point.
Right.
All right, so here are 3 equilibrium constant expressions that we're going to write out for you. The first one is of nitrogen dioxide in a reversible reaction forming nitrogen monoxide and oxygen. Notice they are all gases. Gas, 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 and gas. So the Keq for this is going to be the products divided by the reactants. So it's going to be the concentration of NO, and notice there's 2 NOs.
So we have to square it.
Yep. Times the concentration of O2, all divided by NO2 raised to the power of 2. So again, you can see where the coefficients go.
And I think the reason why, if you're wondering why do we have to square it, is because if you have twice as many particles, they can be involved in that many more collisions. So and it has to do with molecules colliding with each other to cause the forward or the backward reaction.
Yes.
So when you have more of that particular species available to collide, then you have to account for that in the equilibrium expression. All right, so the second one, we have now a reaction between carbon monoxide and hydrogen to give us methane and water. And again, the first thing we're going to look for is, are they all gases or aqueous? And this is an all gaseous reaction, so the Keq becomes pretty straightforward. Okay, we're going to put the concentration of methane multiplied by the concentration of water.
Notice they're both balanced as 1s.
Divided by the concentration of carbon monoxide, multiplied by the concentration of hydrogen, but we have to raise that one to the third power
Yeah.
because of the 3 coefficient.
Yep. So what you can see is this still takes into account the fact that you need to potentially name and be able to balance equations. So again, that doesn't go away, and it should become second nature to you at this point. And the very last equation we have now is phosphorus, solid phosphorus, plus gaseous chlorine in a reversible reaction making phosphorus trichloride, which is also a solid. So we have 2 solids and 1 gas, which means that the KEQ for this, for the
So what do I put in my numerator? I don't have
One.
anything, just a 1.
would be just a simple
Okay, so
1.
the products are solid, so it's 1 over, and there's only one gaseous reactant,
Mm-hmm.
so that's going to be concentration of chlorine gas to the
Sixth
sixth
power.
power.
All right, and that's a special case that we will see potentially again.
Okay, so we're going to do some problems that actually involve numbers, okay, where we're going to find the equilibrium constant, find K, and interpret K. So we're going to you basically write the expression, and then you substitute in the concentrations, and you simplify. Once you've simplified and you get the value for K, as a general rule, since we have products over reactants, if it comes out that it's greater than 1, that means the product part is bigger than the reactant part, so we would say that the products are favored.
Yep.
Okay, if it comes out less than 1, where the denominator is bigger than the numerator, then we would say the reactants are favored. So let's set it up for, this is the same reaction we just looked at in the first example.
So while he's setting that up, I want to draw you back to the idea of the strong and weak acids again. Remember, the weak acids are the ones that had the K values less than 1 because they were the ones that didn't fully go to products. So he's currently has the products divided by the reactants now, and since they are all 1s, the raised to the power of these are all 1s.
So the exponent's just a
Yep.
1, so I'm just going to let it off.
Yes.
All of it.
And now if you plug in the numbers, you have the concentration to be 0.320 times 0.420 all divided by 0.500 and 0.200. And when you hit enter on that, you find the answer to be 1.34.
And that's generally unitless,
Yep.
is that right?
That's
1.34. So we can see that this is bigger than 1, so this is going to definitely favor the formation of products.
yes. All right. All right, so now we're going to look at this in a slightly different manner, where we have the KEQ and we have 3 of the 4 concentrations for the thing given. So using our K equation from the previous slide, we know that KEQ equals 1.34. So 1.34 is going to equal the products divided by the reactants. So we're going to take what we are given and fill it into that equation.
So there is my 2 product concentrations.
We're going to divide it by the unknown concentration of CO2 and by the concentration of water. And
So-
when we solve for this,
So, okay.
all right, so after doing the math on this, we find that the concentration for CO2 to be 7.46 times 10 to the negative 2 molar. This requires the use of some algebra, so you can treat
Yeah.
that CO2 as an X.
Don't forget it's in the denominator, so you have to cross multiply or do something to bring it out of the denominator, which is always fun for students to figure that out. So we can see that it comes out 0.0746 or 7.46 times 10 to the minus 2. So we can work those either way, where we give you all the concentrations, you find the equilibrium constant, or you have an unknown concentration and then you know everything else. Or you can get into ones where you have a quadratic equation or something, or some higher order equation. We won't be doing this year, but that gets into some really funky math doing that.
Yes.
If you take AP chemistry, you'll get to enjoy problems
Yes,
like that.
Chapters like 13 through 16. All right,
All right, so we'll work some more examples of this next time.
have a good time.